All right, welcome everyone who's watching on our YouTube channel. This is our fourth live stream geometry session. So I've really enjoyed all these. And if you would like to join a future session, send me an email at mgreenb801@gmail.com. So I'm going to write that in the description of my video. So we have a number of people here today, I think around 7 from all over the world. So I'm not going to call out all their names, but I want to thank them all for joining. All right, so let's get started. So we have a triangle ABC. And then we draw the end circle. All right. I'm just gonna draw the end center of it, or the end center also, just to make things easier. Let's call it I. Hey Timo, I see you. Just thanks for joining. See if anyone else has popped in.
Hello.
All right, so we just started. So this is the first problem. So we have a triangle ABC. P and Q are on AB and AC, so that PQ is parallel to BC and it's tangent to the end circle. Okay, so basically that means PQ has to pass through like the topmost point of the end circle. All right, so I'm going to rename these P, Q, we'll just call this point R. All right. AB and AC touch the end circle at F and E. All right. So EF. Prove that if M is the midpoint of PQ. So I'm going to draw this so it looks a little nicer. So this is M. Okay. And let's move this. I'm going to minimize this. And T is the intersection of EF and BC. T. Oops. We want to show TM is tangent to the end circle. All right. Looks interesting. Yeah, the diagram, it's like, yeah, let's see if I can make it, maybe that looks a little better. So I'm going to erase that segment just so that we don't already know that TM is tangent. All right. So one thing I noticed is we know that B, C, T, and D are in harmonic conjugation. So I've mentioned this a bunch of times on my channel, but BE, CF, and AD are concurrent by Cheva. So I'll just write this out. Okay. Let's see if I can move this. And so if that's true, then that implies that B, C, D, and T are in harmonic conjugation. So I'll write this out. And yeah, for those of you that aren't as familiar with harmonic conjugation, I have 2 videos on my channel where I just discuss it. So videos 54 and 55, I think it is. I'm not 100% sure. That's kind of where I introduce projective geometry. All right. Yeah, I guess so. Another way we could state the problem is if we take the tangent from M to the in circle, then we want to show that it hits the line BC at a point that's in harmonic conjugation with B, C, and D. I think that might be maybe a simpler way to state it. Do you have any ideas, Timo?
Not really.
Yeah, I think you're the only one on speaker. Let me check, but I think the rest are in the chat. Yes.
Maybe you want to use that PM, Q, and the point on infinity are harmonic.
Yeah. Yeah, let's see if there's a way I could do that. So actually, let me hide this segment or hide point T. What if I instead draw the tangent? Actually, I'm going to cheat a little. I'm gonna hide this segment. What if I just say that? What if I draw the tangent from M to the circle and I call it like T prime, and I want to show that T is equal to T prime. So I see someone just wrote something in the chat. Hold on a second. This is, so to Loon, this is the first problem that we just started. So you haven't missed too much. I3435 says maybe show the tangent to M and N circle is parallel to the tangent to T and the N circle. So the tangent to M and the N circle, well, there's 2 of them. I'm guessing I3435 is saying we want to show that M, because really we want to show that the tangents are the same line. But I think what I3435 is saying is maybe we could show angle PMG is equal to the angle that the tangent from T makes with the N circle. I think that sounds like a decent idea. I forget where I found this problem. Loom is asking where I found it. M is the pole of GR. Yes, that's true. Let's see. Possibly. We could do a polar chase. Let's see. Yeah, how do we use that M as the midpoint? Is there something we can sort of project through? So what if I did this? What would happen if those 4 points were in harmonic conjugation? Is there something we could project through? You have an idea, but we need to set it up differently. What's your idea? Loom is in the chat for everyone. So type it out in a little more detail. I'm a little curious. Yeah, I thought about that. So APQ is similar to triangle ABC. So there's a homophogy taking one to the other. Okay, we define P prime as MG intersect BC. Okay, that's good because I already have that. AR intersect BC. AM and I, no, I don't think AM and I are collinear, but AM and the midpoint of BC are collinear. Yeah. Yeah, M would go to the midpoint of BC. I'll just draw that in. And AR intersect BC, that's where the X circle meets BC, and that's a point where BD is equal to the distance from that point to C. Yeah, I'll just draw in some of the, because it might be useful. Let me draw a segment for that. Okay, so it's a well-known fact that DH is equal to HJ. Is GR parallel to EF? That would be interesting. I don't think that's true. It doesn't look true from the diagram. We do have that EF. I think, is this the Iran lemma, that AH, EF, and RD are concurrent? I know we were talking about the Iran lemma on the Discord server. No, it's probably something similar with the end center, but that's not the Iran lemma. Okay. All right, so is there anything we can project through? I'm wondering if we like project through point G onto PQ. So T would go to M. No, that's not going to do much. T is the pole of GD. Yeah, that's true. T prime, we're trying to prove that T prime F and E are collinear. If we can prove that that's the case, we would solve the problem. Is A, G, and D collinear? That would be interesting. Let's check that out. Ah, that looks true. Yeah. Okay. How do we show that A, G, and D are collinear? Ah, spit it out. We got a fancy theorem here. That's what Lynn's saying in the chat. Bricard. I've used Bricard before on my channel. Let's see. So if A, G, and D were collinear, I'm just thinking what that would look like. Okay. How do you solve it using a polar chase? T lies on the polar of A. Yeah, so if the initial T lies on the polar of A, that's true. But not necessarily this T prime. Yeah. Yeah, you kind of, since I've kind of redefined P prime here, you have to be careful with what you know versus what you're trying to prove. I don't see it right. Is it obvious that if A, G, and yeah, by the theory of poles and polars, if we can show A, G, and D are collinear, that would solve the problem. Let's see. Yeah, so I3435 kind of is reiterating the idea of taking a homothety, taking triangle APQ to ABC. So yeah, I'm just trying to think. Oh, I think I see it. So MG is equal to MR. Yeah, we put this, so if we reflect R over point M, I think this is essentially it. So reflect R over point M, so we get R prime. And then using the homothety, so actually, first of all, I'm going to note that this is a right triangle right here. So MR is equal to MR prime is equal to MG. So let's see what that means. That means angle R prime GR is 90 degrees. Okay, let me just write an angle. AM is perpendicular to GT. Also, so by the homothety, so I'm just gonna write out some stuff for the viewers. So I'll just say it's well known that DH equals HJ. And if you haven't seen this, I did a video on it, so you could look at my video on the IM lemma, which is on my channel. So that basically means that R prime corresponds to D, and so AR prime and D are collinear. Okay, so AR prime and D are collinear. Can we show that R prime? Can we show that AR prime and G are collinear, or A, G, and D are collinear? Let's see. Yeah, because, or actually, I'm going to show R prime, G, and D are collinear. I think this might be what Loom is saying. So we know angle DGR is 90 degrees because DR is a diameter. So is it D? Yeah, DGR. It's equal to 90 degrees. Okay. And if that's true, that means D, G, and R prime are collinear. All right. So I'm going to draw that in. And like I mentioned before, we also know that AR prime and B are collinear. So in fact, we can add point A to this. I'm just going to add A here. Okay. And so if that's true, that means T prime lies on the polar of A. Since T prime G and T prime D are tangent to the circle. So all right. And that means that A lies on the polar of B. I should say A lies on the polar of T prime. And so, oh, actually, I should have written A lies on the polar of T prime up here. Let me swap these two. How does the process of finding GEO problems go? So I use a certain website. I'm just going to show Loom very quickly. It's imogeometry.blogspot.com. And this really nice website has geometry problems from a whole bunch of different competitions. So like if I wanted to look at China team selection test, for example, it has all the problems in geometry going back really far. So it's a really nice resource. So that's kind of how I go about finding the problems. And this website was put together by a user Parmenides on the Art of Problem Solving forum. So I think his name is Takis Chronopoulos or something like that. So that's how I find these geometry problems. All right, yeah, thanks for the question. So T prime lies on the polar of A. So T prime, E, and F are collinear. Because A, E, and AF are tangents. And so that means T prime equals T, and that solves the problem. So I'm just going to write that out. T prime equals T. So Tm is tangent to omega. All right, thanks everyone for the help on this. This is a fun one. I like that I got to use poles and polars. So for those of you that don't know about poles and polars, I have 2 videos on it on my channel, I think 65 and 66. So if you haven't seen it, check it out. All right, so that's the first problem. Let's move on to the next one. Whoops. Yeah, share it. You can share it in the Discord channel, Loom. All right. So let omega be the circumcircle of an isosceles triangle ABC. Hold on just a sec. What am I doing? Okay, so we have an isosceles triangle ABC. I'm not sure. I do think I did look at the problems from Iran team selection test when I was choosing these. So it could be from Iran, I don't know. Yeah, I should probably write down where I find each of the problems. Whoops. Okay, P and Q lie on, okay, so omega is the circumcircle. P and Q lie on omega and BC. So I'm just gonna, so Q would be the point on BC. So AP is equal to AQ. All right, whoops. I keep hiding stuff that I don't want to hide. All right, so AP equals AQ. AP and BC intersect at R. All right, let's hide some stuff. Prove the tangents from B and C to the inner circle of AQR meet on this circle. Okay, so I'm going to draw the inner circle of AQR. There we go. And I'm going to draw the tangents from B and C to it. And it happens they do concur on omega. So I'm gonna reframe this. Is it Poncelet's Porism? I think you might. Let's see. Yeah. Okay. You guys are pretty fast. So just for the viewers, I'm gonna write out a proof of Poncelet's Porism using Euler's formula, because I think this might be a good place to teach it. Let's see. So, what? Hold on a sec. So this point was D. So I'm actually, hold on a sec. So we have this circle that's inscribed in BCD. So if you look at triangle BCD, so really we don't know the, we haven't proven it yet, but okay, so it was from my random team selection test. But in triangle BCD, this is the inner circle and that's the circumcircle. So I'm just trying to see how would we apply, so Poncelet's Porism basically says if we let AQ meet the circle at another point, E, and it says PE would also be tangent to that circle. Okay, so hold on just a second. All right, so here's what I'm gonna do. So when you guys say to use Poncelet's Porism, I'm guessing you're saying first. I guess, yeah. I don't know if it's that easy to just apply Poncelet's Porism. Yeah. So if I let AQ meet the circle at a point D, can we show PD is tangent to that circle? Okay, you called it point E, so I'm gonna take your word and call it E. Can we show PE is tangent to that circle? Hold on, everyone. I'll be right back. Just a second. All right, I'm back. Okay, maybe AD equals AR. Or AE equals AR. You're trying to prove that. No, you're saying it is true by the shooting lemma. Okay. Hold on just a sec. Let me think through that. So we know AP is equal to AQ from the problem, right? Is it obvious that AE is equal to AR? I'm wondering if that's just like a power of a point. So we have, AQ times AE is equal to AP times AR by the shooting lemma because A is the midpoint of arc BC. Okay, hold on just a sec. Trying to think through that. So is it true that AQ times AE is AB squared? Yeah, okay. So AQ times AE is both AB squared and AC squared. Okay, okay, yeah, inversion. So I'm gonna write this, here's how I'm gonna write it out. So I'm gonna prove that AE is equal to AR. Okay, let me make some more room. Okay, so we can show that triangle ACQ is similar to ABC. That's true by an angle trace, so I'm just going to write it. So this is basically what I3435 is saying is a shooting lemma. And so that means that, so from those similar triangles, it's not hard to show that AC squared is equal to AQ times AE. And then at the same time, triangle ACP, I believe, is similar to a RC. Is that true? I'm not sure if that's true, actually. No. Yeah, I'm trying to show that AC squared is AP times AR. Oh, well, that would have to be true if those triangles were, yeah, no, that's true. Okay. All right. So that means we have AC squared is AP times AR. And so since AP equals AQ, then AE equals AR. right. Now, if we know that, where do we go from there? Can we show that EP is tangent to the smaller circle? So yeah, I kind of just did it the long way, but if you know about inversion, if you know about inversion, that would kind of give you a shortcut to these conclusions. Whoops, didn't mean to do that. Okay. Okay. This makes a lot of sense. So basically, one of the viewers just told me this privately, but basically we have a symmetry. So if AQ is equal to AP and AE is equal to AR, then by symmetry, since PQ is tangent to this circle, I guess we could give it a name, but then PE has to also be tangent to that circle. So I'm going to call it gamma, but so by symmetry, PQ is tangent to the incircle gamma of triangle AQR. So we know that, but that would imply that PE is also tangent to gamma. All right. So I'm going to draw that tangent segment. And now's the part probably where we could use Poncelet's Porism. Yeah. So since there was all this work first, yeah, I'm gonna actually write out the proof of Poncelet's Porism also, but basically, let me write it out this way. So QR is tangent to gamma, not PQ. Oh yeah, sorry, my bad. This should be QR. Thanks for the correction. So triangle AEP is inscribed in gamma, and I'm sorry, it's inscribed in omega and circumscribed about gamma. So by Poncelet's Porism, So I'm going to explain what Poncelet's porism is in just a sec. See, someone wrote something. Now we can remove R and just look at the cyclic points. I'm not sure. Okay, are you still saying to use Poncelet's porism? Yeah, Poncelet's porism finishes it. So yeah, I wrote out the last step here by Poncelet's porism. But basically, Poncelet's porism, it says that if you have two circles, so in this case, the two circles in the diagram, if you have one triangle, which is circumscribed in one of the circles, but circumscribed about the other circle, it says if there exists one such triangle, then there actually exists infinitely many such triangles. And it says that basically for any point on the outer circle, if you take, so for example, yeah, so in this case, Poncelet's porism, it actually applies to conics, I think, not just circles. But let's say I pick any random point D on the outer circle, and I draw the two tangents to the smaller circle. Then Poncelet's porism says that if I connect these two intersection points, so I'll call it F and G, it says that FG is going to be tangent to the smaller circle no matter where you place point D. So basically, if we take the tangent from D to the smaller circle, and we let it intersect the circle at D, then if we choose D to be that point, then Poncelet's porism says basically that CD would also have to be tangent. So there's a little bit of a lesson that I'm kind of skipping over here, but I'd recommend looking up this theorem if you haven't seen it. It's really interesting, and it can be proven, I believe, without too much work using Euler's theorem. So I'm just going to write this out. So you can prove Poncelet's porism. I think IO squared is equal to R times R minus 2R. I'm not sure if I'm remembering that exactly correctly, but this is actually a very old IMO problem to prove that IO squared is R times R minus 2R. And from there, I'll just let the people viewing it on YouTube see how you can prove that. I ran team selection test as a bunch of problems that use Poncelet. Interesting. All right, so I'm going to move on to the next problem. We've spent a while on this. Hold on just a sec. Oops. All right. Let gamma be the circumcircle of isosceles triangle ABC. We have another isosceles triangle. Okay. But this time C is the vertex. All right. An arbitrary point M is chosen on segment BC. And the point N lies on the ray AM, and AN is equal to AC. Okay, so I'm going to draw a ray. AN is equal to AC. And then we draw the circumcircle of CMN. Am I missing something here? AN is equal to AC. Then we draw the circumcircle of CMN. And we see where it cuts gamma. And we say it cuts it at a point P. All right, and A, B, and CP intersect at Q. So I want to make sure Q lies on the screen. See how I can draw things to make that easiest. Just draw it like that. A, B, and CP be the Q. I think, yeah, it should turn gray instead of blue. There we go. Gray means it's a defined intersection point. We want to show angle BMQ equals angle QMN. Let me check this out just to make sure I didn't make a mistake. If I use GeoGebra's tool, where is it? There we go. So this is cool. We both use Poncelet's Porism today, and we use poles and polars. Yep, it's true. All right. So we want to show MQ bisects angle BMN, basically. Someone wrote something in the chat. You have an idea for this, all right? Okay. So ACQ is our initial triangle. Hold on just a sec. Okay. Let me just try to digest this for a second. But yeah, I mean, if you haven't seen this problem before, I wouldn't call it spoiling. Like maybe you could see the solution really quickly. Let me see. QM is the bisector of CQA. Oh, that looks like it's true. No, QM is not the bisector of CQA. That looks really close, but it's not. At least I don't think it was based on that. Yeah, no. Okay, so QM you're saying is like the median line. That would be kind of interesting. So basically you're saying if P is the midpoint, then you're saying angle MQC is angle DQA. They're so close, it's yeah. Oh no, one's showing 19.8 degrees and the other's showing 19.6. Look really, I'm guessing that must just be the inaccuracy of GeoGebra. Wait a sec. Now they are looking more different. I'm not so sure if that's true. what Loom is saying. It might be. Maybe I just messed up somehow. Is that true that QM is like a Symedian line in triangle ACQ? You believe GeoGebra more. Yeah.
Maybe we let MQ intersect the circumcircle of PMC, and then we know A, B, M at this point are concyclic.
Okay, I'm going to try that. What were the points you were saying?
A, B, M, and D.
Okay, so you're saying A, B, M, and D would be cyclic. Let me just think about that. Is that power of a point? Yes. No, that's radical axis theorem. Okay. So I'm going to write that out. Sorry, there's so many people in chat. Can you please define the circle of CMA? I'm just curious. What is MMP? So moving points. I'm gonna avoid moving points, but thanks for the idea. I appreciate it. All right, I'll draw the circumcircle of CMA, but I'm gonna write out Timo's idea that AVMB is cyclic. So hold on just a sec. Yeah, unfortunately, yeah, I don't want to cut. Let me see if I can. Yeah, I'll do this. Okay. So, whoops. Just trying to make room so I can. So we have Q. So I called it D. Okay. All right, so that's by power of a point. So ABMD is cyclic. That's kind of like the way that you prove the radical axis theorem. All right. ABMD is cyclic. Let me check out the chat just because I know I probably missed a few things. Rimes theorem. So angle BMQ is equal to angle BAB. So basically we want to show angle BAD is equal to angle BMA. That's what it looks like. Sorry, before I read the chat, I'm just gonna try some. So BAD is 47.3, DMA is 47.3, and that would also be DBA, right? Would be 47.3. So we have a lot of 40. Basically, we want to show DAB as isosceles, right? Is that obvious? Is D the circumcenter of ABC? I don't think so. No, but we just want to show DAB as isosceles. Let's see. QD intersect CMA. Sure, I can do that. All right, so we want to show that DBA is isosceles. Is D the in-center of ACM? I feel like D might be the in-center of ACM. Let's see. Yeah, that's looking pretty true. Yeah, now maybe we could use stuff like, does EC equal EA equal EB or something? Let's see. You also move M around to see if D moves. Yeah, it does. I think D is the in-center of ACM. I'm trying to see how I can prove that. Is that just like an angle chase or something? Because that should solve the problem. CD is perpendicular to AB. Yes, exactly. If we can show D as the in-center of triangle ACM, then it would be true that CD is perpendicular to AB, and that would solve the problem, right? I'm just trying to think how we do that. Have we used that AN is equal to AC? We've never used that fact. That has to come into play, right? Inversion bash. What would we invert? I feel like I'd rather not do too much of a bash here because I feel like we're very close. Let's see, is E the midpoint of arc AC? Let me check this out. Yes. If we can show E is the midpoint of arc AC, like there has to be a way to show D is the in-center of triangle ACM. I feel like it's probably pretty close. In order to use AN is equal to AC, can you define CN intersect AQ? I could try that. Is CNAB cyclic? I don't think so because N doesn't lie on the circumcircle of ABC.
We can say D prime is the in-center in AMC, and then with an angle chase we get AD and B are concyclic.
So yeah, that sounds, I think that should do it. So I'm gonna go delete, I'm gonna go delete this circle, just for now. Okay, so we know ABMD is cyclic, and then Timo is saying if we let B prime be the in-center of ACM, and by an angle chase we can show that AD prime D is cyclic. That's what you're saying, right?
Yes.
And would that be enough? So that would mean that D prime would, I'm just thinking ahead a few steps. That would mean D prime lies on this circle. Would that be enough to finish it off?
In the same way, D prime lies on the circle through CM and P, and then by radical access theorem, we are done.
Okay. So we'd also use an angle chase to show that CD prime MP is cyclic. is what you're saying?
Yes.
All right, so I'm gonna hide a bunch of stuff here. P point M. All right, so I'm gonna let D prime be the in-center. I know there's a shorter way than drawing all the angle bisectors. Like I think I3435. So there's some GeoGebra command where you can just say triangle center of ACM, but I'm just gonna skip it for now and just do this. Triangle center AMC1. All right, so next time I will try to remember that, but for now I'll just do it manually. So D prime is the in-center.
I wrote the angle chase in the chat.
Hold on just a sec. Whoops, what do I do? I don't want to hide point D, I just want to hide these. Hold on just a sec, I got to do something. All right, I'm back. The angle chase in the chat, let's see. So, just gonna type it out for the viewers. All right. AD prime M. Yes, the first fact you could get using an angle chase that's not too difficult. And then I'm just going to write, just to be super picky, if B prime is the in-center. Right. Okay, so these are both fine angle chase. I'm not going to write up the whole angle chase. I'll just write this since I think it's not that hard to do. So that means that AB prime MB is cyclic. Hold on just a sec. That's CD prime M and C. Hold on just a sec. So I could see why AD prime MB is cyclic. Now I'm looking at CD prime MP. Or CD prime MN, is it? I'm sorry, I already forgot.
Yes, CD prime MN, and you can get this by exactly the same way. because we have AC is equal to AN.
Ah. AC. Okay, so so I'm going to draw that in. And then angle ANC is equal to angle ACN. Is that right? Are those the two that are equal? Yeah, AN is equal to AC. Whoops. And you're saying that that's 180 minus DMN. So T prime MA. That's also by an angle chase. Right, and so ANM, I'm sorry, CD prime MN is cyclic. And so D is equal to D prime. So I'm going to draw in those two circles. Did we ever show that? So D is equal to D prime. And then we can finish the problem off very easy from there. So angle BMQ is equal to angle DAB. And that's equal to angle DBA by symmetry. And hold on just a sec. So yeah, let me just draw this segment in. I'll call that D because we know D prime is D. I'm trying to remember what we were initially saying, why that would prove it.
Because this DN center, we have CMD is equal to DMA. And this is exactly what we want to show.
CMD is equal to DMA. Oh yeah, that's right. I think I thought about it in a more complicated way before, but that is simpler than what I had thought. And my brain is just not working right now. All right, so all right, so I'm going to move on to the next problem then. This is a pretty nice one. All right. Let me see. I might have missed something in the chat. I think Loom may have had a different solution. I'm not sure. But yeah, you can post it on the Discord channel after if you have other solutions. Because yeah, I'd really be interested. Hold on just a sec. All right. So we have triangle ABC. AB is greater than AC. The tangent to the circumcircle at A intersects line BC at point P. Let Q be on AB so that AQ is equal to AC. Oh, but it's past, A lies between B and Q, okay. So Q is really on line AB, okay. All right. Let R be on AP so that AR is equal to CP. So for this, I have to use the compass tool. Whoops, I don't need to do anything here, just hide the circle. Let X and Y be the midpoints of AP and CQ. We want to show that CR is equal to 2XY. All right. Let me check the chat. Is PQ parallel to XY? Let's see. Looks plausible. I think it is. Not 100%. Oh, no, I don't think so. Yeah, no, PQ is not parallel to XY. That's an interesting idea. Yeah, maybe I could, let me try color coding some stuff just for fun. So, let me check the chat. Concurrent triangles. Is QC tangent to the circumcircle? It kind of looks tangent, although that would be, let's see, maybe it is. No, QC is not tangent. It looked tangent in that diagram, but not necessarily. I'm gonna try something here just for fun. Can I do segment AQ? Whoops. How do I choose?
$1.5 घंटा था, हो गया। हुआ नहीं, 1.5 घंटा, 1 घंटा 15 मिनट हुआ है।
Oh, what?
शायद 1.5 घंटे की क्लास है। इसकी और
I'm sorry, Kay, were you trying to say something? Kay, I'm sorry if I missed what you had to say. Oh, all right. Can you define CQ intersect AP? I could. You think CA is tangent to AQX? Interesting. I can try that. Is that really tangent? AQD. Oh, okay. Hold on just a sec. I'm just looking at everyone's suggestions in the order they're giving them. It does look tangent. Let's see. Yeah, that looks like it's always tangent. Okay. Let's see if we can prove that. I'll draw the circle, but we have to prove that CA is actually tangent. We want to show RC. Let's see. Is it obvious that? Is it just an angle chase that shows that CA is tangent? Okay, I'm gonna hide the circle for a sec just because, yeah, I don't want to show it there until we prove that AC actually is tangent. But it might just be an easy angle chase because we know AP is tangent, right? So angle CAP, you need to prove CB is equal to CQ. Then that would prove the tangency. Is that true? Q looks very close, but looks, no, CB is not necessarily CQ. Hold on one sec, guys. I'll be right back. All right. Let's see if anyone said anything in the chat while I was away. Is AQPC cyclic? Yes. And if that's true, that means CQ and QY are isogonal. I don't see all this right now, but I believe you. Let's see. First, I'm going to try to show that AQCP is cyclic. I think that should just be an angle chase, right? Feels like it, yeah, because
I don't think AQPC is cyclic.
yeah, just as you said that, I don't think it is. Yeah, P does not lie. All these points are so close, it's really funny. But yeah, AQPC is not necessarily cyclic.
Let's define the point on AB for which AC is equal to A in this point.
Okay, so that would be like a right angle. So
yes.
Yeah, okay. 1 sec. Let's call it Q prime, why not? So the reflection of Q over A. And so then we have a right angle.
And we know AQ prime R and ACP are congruent.
Did you say AQ prime R and ACP? Yeah.
Yes. Yes.
All right. And that's where we use that AR is equal to CP. Okay. I am going to write that out. Let's move this to the side, maybe shrink it just a little bit so I have room. Right. All right. And then Q prime AR is equal to ACP. And then so AR equals CP means those two triangles are congruent. All right, let me check. Y is the midpoint of DR. Is that obvious? Oh, I actually think I switched X and Y in the problem statement, but I don't even think it matters. I'm just going to switch X and Y back just to match the problem. But yeah, it doesn't matter. You check if X is the midpoint of DR. Let's see. I think it is. Yeah, that looks like it has to be the midpoint. Okay. So that would basically mean that we want to show AD is equal to RP. Check out. So now reflect D over Y and prove that RC is equal to RD prime.
If we can prove Q prime CR and AYX are similar, we are done.
Okay, so we want to show that AYX is similar to QCR.
Q prime CR.
Q prime CR. Okay.
And we know Q prime C is 2 times AY. And so CR is 2 times YX.
Ah, I see what you're saying. I'm just going to do what Loom said, just so reflect D over Y. I don't think you're using the point D prime here, but Loom was suggest maybe Loom has a different idea. Okay, so Timo, your idea is let's see, Q prime CR is similar to AXY. Yeah, I wonder if we can use side angle side similarity to show that. Is QR parallel to BP? I'm sorry, Q prime R?
Yes.
Yeah, those are parallel. Do you see why they're parallel?
Yes, because we have the congruent triangles, and ACP and ABP are similar. And so AQ prime R and ABP are similar too.
Okay, so I am going to write this out. So just thinking of the best way to do it. And AC over AB is equal to AP over AB. I'm just saying, it is equal to CP over AP. Okay. So that's by similar triangles. So I'm gonna write this out more fully, but CP over AP is equal to AR over AP. Okay. So this is kind of what Timo was saying. All right, so
I think I got the solution and we don't need this parallel aspect.
Oh yeah? All right, hold on just a sec. All right, let me check. No, CA is not equal to CP. Let's see.
We know Q prime C is 2 times AY.
Okay.
And Q prime R is 2 times AX. And with an angle chase, we get CQ Q prime R is equal to XAY. And
Okay.
so Q prime CR and XYA are similar triangles with a factor 2, and therefore XY is equal to CR. And XY times 2 is equal to CR.
So how do you know that Q prime R is twice AX?
Because Q prime R is equal to AP, and X is the midpoint of AP.
And Q prime R is equal to AP because of the congruent triangles. Ah.
Yes.
Okay, so we can erase some of this. All right.
And I think I have to go now, so
All right.
you can finish the solution with the rest of the team.
Yeah, thanks for going on the call. Yeah, I really appreciate it. Have a good rest of your day.
Thanks.
All right, see you.
See you.
See you. All right. So I'm going to finish writing out what Timo had to say. So because these triangles are congruent, we have Q prime R is equal to AP, which is equal to 2 AX. And then also Q prime C is equal to 2 AY. And that's because all right. Hold on just a sec. And so then we want to try to show that angle AYX is equal to angle Q prime CR. And Timo said that that should just sort of be an angle chase. I think he's right. I'm just sort of thinking it through in my head here. Lumet. All right, let me see. Can we show that angle RCY is equal to angle DYX? Okay, we want to show that angle RCQ is equal to angle AYX, but both of them have sort of a 90-degree angle contained in them, right? So we want to show that angle RCY is equal to angle DYX. Let's see. Okay, let me write out some stuff here. Hmm. Sec. I'm going to draw in. I'm going to draw in the two congruent triangles. Okay. So we want to show angle Q prime CR is AYX. Just reiterating it. Does anyone see why that's the case? I think Timo was saying it should be not that hard of an angle chase to show that Q prime CR is AYX. But then you could subtract 90 from each of those two angles. Let me check it out using the measurement tool. BQ prime C and AYX. Whoops, sorry. So I'm guessing you're saying those are similar triangles, BQ prime C and AYX. So Q prime AC is equal to YAX. I think he was saying that Q prime CR is similar to AYX, and that would solve the problem. That's what he was saying. By the way, YXCQ is cyclic. YXCQ prime. I'm just going to write that out. Y. Or I think you mean YXCA, right? And if that's true, I think that would get us to what he was saying. Not 100% sure, but I think so. But it looked like YXCA was cyclic. Let me check if that's really true. Actually, I'm not 100% sure that's true. Could just be, yeah, no, that's not true. But yeah, it doesn't seem super obvious to me. Timo was saying angle AYX is equal to angle Q prime CR. Maybe I'm just not seeing it. Oh, Raffaello, do you have an idea? Let me look at the comments. Don't we want to show XAY is equal to CQ prime R? I guess so I was thinking side angle side similarities, but so I was thinking Q prime CR is equal to AYX, but that would still help. I think that might get us there if we could show that. Yes, RQ prime is parallel to BP. I showed it before. I think I might be getting pretty close actually to figuring this out. Yeah, I think it's an angle chase if I show the parallelism, but yeah, I'm not sure. Without the parallelism, I'm not sure. Let me write out what I wrote before with all the, yeah, let me write all this out. I think this helps. So yeah, I see a way to do it with the parallel lines. But yeah, I think Timo had an idea without them, but I'll let him write his idea on the Discord server. D prime R intersect PZ. D prime R intersect BP. I'm just going to look at Bloom's idea very quickly. ARBZ is cyclic. So Loom in the chat is saying that this is cyclic. I'm not sure if it is. No, that's not a cyclic quadrilateral. I'm just going to finish off the proof. If you guys have other ideas, feel free to post them on the Discord channel or in the comments of my YouTube video. Basically, this means that Q prime R is parallel to BP. Okay. And then so So I'm going to draw that in. And then we have, I'm going to write out kind of what I did before. So we have QC is equal to 2AY. All right. And then we also have QR is equal to I'm trying to remember what I said before. So I said that QR is 2AX, right? Because QR, oh yeah, so QR is equal to AP is equal to 2AX. And that's because QAR is congruent to ACP. That's why QR is equal to AP. And then we can show a third angle is equal. So I can see why angle YAX is equal to angle RQ prime C. We'll check the chat. So let's see. So thanks for joining, Erie John. We'll see you next time. All right. Q prime C is equal to 2AY, and QR is equal to 2AX. Yeah, but you have to show. So I'm just telling Loom. You have to show that you'd have to show that a pair of angles are equal in those two triangles first before you can conclude that CR is 2XY. So here was kind of what I had in mind. All right, so I'm going to break this up into two lines. See how this comes out. All right. Let's check out the chat. All right. See you, Loon. Thanks for joining us. It was fun. All right. There should be Q prime everywhere. All right. So basically, we kind of have like two similar sides and a similar angle. Let me see who's in the chat still. All right, we still have 3 other people in the chat, but Timo left. So Raffaello and Ann Mull are still left. I think this is going to be the last problem I do. Okay. Oh, that's enough to do it. That is the angle we want. I don't know why I got so confused. So that solves it by side-angle side similarity. I don't know why I was thinking we wanted to show AYX is equal to Q prime CR. But yeah, that finishes it off. So then we have triangle YAX is similar to triangle RQ prime C by side-angle side similarity. Yeah, I don't know. I got confused. And so that means that CR is equal to 2XY. All right. But I did have to use this parallelism in this angle chase. So I'm curious if Timo had a way that doesn't use that parallelism. Maybe he could